Hi folks, I'm going to make a recording of the Unit 3 test solutions just so you guys have a bit more explanation than just looking at it, especially for there was a number of questions where there was multiple choices, multiple correct solutions, especially for, say, equations of planes and that kind of thing. So the first question, we want an equation of a line that's perpendicular to this plane and passes through this point in symmetric form. Most people did this one all right. So there's my plane. Remember that the normal to this plane, that is the line that's the vector that's perpendicular to this. So my normal from the Cartesian form is 2, -3, 4. And that's going to actually be the direction vector of this line. So I've got some line that also, that's very not straight, that also is perpendicular to the plane. And we have, say, some point, -2, -1, 4 on that line. So the equation of the line, remember, we just use our position vector, which is our point, -2, -1, 4, plus t times our direction vector, which will be the normal to the plane, 2, -3, 4. And we want to put that into symmetric form. So I would put it into parametric, x equals -2 plus 2t, and y equals -1 minus 3t, and z equals 4 plus 4t. And then I'll rearrange each of these to solve for t. So x plus 2 over 2 equals t, and y plus 1 over -3 equals t, and z minus 4 over 4 equals t. And then we would just set all of these equal to each other. So the symmetric form is x plus 2 over 2 equals y plus 1 over -3 equals z minus 4 over 4. And that's my solution for that one. The next one, this one did have a typo. When I had done my solutions, cutting up the questions, I had it so that was a -4, and these would have been two parallel lines. So I'm going to do the solution to this because I think that it is a really valuable question for you guys to be able to understand. But if you did the redo, then it was very similar to this. If you did found that these lines were skew, then that's, also a good thing to be able to do. But I do want you to have the solution to what the question was intended to be with that -4. So we see here that L1, we've got a point which is -1, 5, -2, and we have a direction vector along that line that's 3, -1, -1, 2. And then we've got L2, which there, and we have a different point, let's call that point 2, and this would be the point 4, 0, 5, and we have a direction vector along this line that is -6 to -4. So we see that the direction vectors, M2 is -2 times M1 for my direction vectors. So you kind of see there and there that those are scalar multiples. So I can't use them both in the equation of the plane. So here I need to find a different direction vector, and I'm going to use these 2 points to find my other direction vector. So P1, P2, I'll just call that, I don't know why that's not going, and find that red vector between those two. So 4 minus -1 is 5, 0 minus 5 is -5, and 5 minus -2 is 7. So that would be my other direction vector that I would use. So I'll use one of the two, either one of the points, and the new direction vector. So I can pick either one of these 2 points. It does not matter at all which one you pick. I'll pick the 405. So 405 plus S times one of my direction vectors. So I'll use that red one that I drew in there, plus T times either one of the other two, the 3, -1, 2, or the -6, 2, -4. So S and T can be any real number. Then we need to figure out the equation of this in Cartesian form. So we need to do the cross product of the 2 direction vectors to find the normal. So we've got -10 minus -7, and 21 minus 10, and -5 minus -15. So my normal, that would be -3, 11, and 10. So then I would say that that's -3x plus 11y plus 10z plus d equals 0. And I'm going to sub in my point, the point 405 that's on this plane, and use that to solve for d. So -3 times 4 plus 11 times 0 plus 10 times 5 plus d equals 0. So -12 plus 50 plus d equals 0. D equals, that would be -38. So I'm going to take that and rewrite my equation. -3x plus 11y plus 10z minus 38 equals 0. Now you have to be careful here that we put Cartesian equations in the proper form, and that can't have a leading negative. So I'm just going to multiply through by a -1. 3x minus 11y minus 10z plus 38 equals 0. And that would be my equation of the plane in Cartesian form. And here we're going to find the intersection of the 2 planes if it exists. Remember that the intersection of 2 planes is a line. We do know that these planes will intersect. I would say that normal 1 is not a scalar multiple of normal 2. Therefore, they intersect in a line. So there are actually an infinite number of ways to find the equation of that line of intersection. So remember that there's no unique form of a line in R3, especially if we're looking at that vector equation. So this one, people kind of did this in a number of different ways. Some people kind of looked at this and said, hey, that's really easy to eliminate my z. So they did, for instance, let x equal t or let y equal t. And that actually probably is a better strategy. It makes it a little bit easier in the elimination step. I do think most people here said let z equals t. So I'm going to go with that, even though it may be a little bit quicker to eliminate z, just because I think that that's the most common. So I would say let z equals 0 plus 1t. So remember, we want to find our line of intersection, and it's a point, a position vector, plus t times our direction vector. And we're just kind of arbitrarily saying we're going to find the point on the xy plane and the direction vector that has a scalar multiple where t is 1, or z is 1. So then I need to do some elimination to get rid of one of these variables, x or y. So I'll multiply that second equation by 2, or whoops, yeah, you know what? I'm going to multiply this one by 2. So equation 1 times 2 gives me 8x plus 2y minus 2z equals 4. And then I'll just keep x minus 2y plus z equals -3. And I will add down. So I've got 9x minus z equals 1. Now I know that z equals t. So I get 9x minus t equals 1. So 9x equals 1 plus t. And then divide out that 9. X equals 1 over 9 plus 1 over 9t. So that gives me the other piece of this vector equation. I've got my x component of the position vector and my x component of the direction vector are both 1 over 9. I would take equation 1, I think, because that's got just a y and not like that negative 2y. Might make my calculations a little bit easier. I'm just going to rearrange it in this step and say y equals negative 4x plus z plus 2. And then I'm going to sub in the x value from here. And I'm going to sub in my z value from here and just simplify that out to figure out y. So I get negative 4 times 1 over 9 plus 1 over 9t plus t plus 2. So negative 4 over 9 minus 4 over 9t plus, I'll make this 9 over 9t plus 18 over 9. Just kind of common denominator it all up here. So then I've got 14 over 9 plus 5 over 9t, and that is my y. And then I can take those components and put them into my vector equation. And it doesn't specify any different kind of equation here, so we can just leave it as is. That's all set for number 3. For number 4, there are an infinite number of possible solutions here. So we want to get a vector equation for the plane 3x minus 9y plus z minus 1 equals 0. So we know that the vector equation of a plane is r naught plus s times vector a plus t times vector b. Now, the first one is our position. So x naught, y naught, z naught, this point will satisfy the Cartesian equation. So if you substituted in those points, it has to work in the Cartesian equation. That's a point on the plane. And for A and B, these are vectors on the plane. So A dot n equals 0 and B dot n equals 0 because they're perpendicular to the normal. So from here, we just need to find one point on the plane, and that can be any point. So to find r naught, I think probably the easiest would be to say, well, what if we wanted to find the point where this plane intersects, say, the xy plane? So, or actually, you know what, I'm not the xy plane, intersects the z-axis. I'm doing the z-axis because when I look at this, I've got a coefficient for the x and a coefficient for the y. So let's say I want to find the z-intercept of this plane. So x equals 0, y equals 0. We just have to solve for z. So then 3 times 0 minus 9 times 0 plus z minus 1 equals 0. So z equals 1. So that's a point on my plane. That can be my position vector. Then I have to find two direction vectors, and they need to have a dot product with the normal that equals 0. So vector A dot negative 9 and 1 equals 0. And we need another vector for B dot 3 negative 9 1 also equals 0. So you can kind of fiddle around and put any numbers in there as long as the dot product equals 0. And remember, you're going to multiply the x's, multiply the y's, multiply the z's, and add them all up. So you might notice, hey, I've got 3 and -9. And 3 times 3 is 9. So maybe you want to kind of make a 9 here by putting a 3. So then when you multiply the x's, you get 3 times 3. And here you've got -9. So that can like balance out if you multiply that by 1. So here you'd have 3 times 3 is 9. And 1 times -9 is -9. And 9 minus 9 is 0. We don't want anything else happening from the z, so I'll put a 0 in there. That's one direction vector. You could do kind of a similar thing. It's always easier if you throw a 0 in. I might put a 0 there. And then I need x times 3 plus y times 1 to equal 0. Well, what if I put a 1 there and a 3 there? Then I would get 1 times 3 is 3, and 3 times 1 is 3. That's going to add up to 6. I don't want it to add up to 6, so we'll make one of them negative. Now I've got -3 plus 3, and that's 0. So you just have to kind of like wiggle them around and try and play with those numbers a little bit as long as the dot product equals 0. So then my vector equation for this plane would be take that point on the plane plus s times one of my direction vectors plus t times the other one. And you certainly didn't need to write this much. Just kind of, people maybe would write like that much and this much, but this is just kind of the explanation up top. Here, create a system of 3 planes that would model case number 4. So remember case number 4, and I should have copied this picture in because I'm going to probably make a mess of drawing it here. Case number 4 is like this. There's 2 parallel planes and then 1 plane cutting through them. So each of those pairs of planes would have a line of intersection, but there's no solution altogether for all 3 planes. So we know that plane 1, let's label them like that. So the normal of plane 1 would equal a scalar multiple or equal the normal of n2, but that the d values would not be equal. The Cartesian equation would not be exactly the same. So for instance, you might have x plus 2y plus 3z minus 10 equals 0, and then 2x plus 4y plus 6z plus 7 equals 0. So you can see that the planes are parallel. Their normals are scalar multiples, but they have way different d values. And then the last plane, plane 3, can just be anything that's not a scalar multiple of that. So it might be 5x minus y plus 7z minus 8 equals 0. It could be anything else as long as the normal's not a scalar multiple. So most people chose A, I would say, when solving this question 6 where you had a choice. And most people did this using matrices. So here we've got 1, 3, -1. Now, a common mistake here, remember that you have to have it equals to that number. You have to put the system in like this line kind of represents where the equal sign is. So you would have to bring that 9 to the other side and it would be -9. A couple people had that error. Then 1, -1, 1, +11, and 1, 2, 4, and +5. So my first step, I would eliminate, this one's kind of nice. You've got nice, like just ones there. So I'm going to say R2 equals R2 minus R1 and subtract that out. So the first row is not changing at all. And subtracting out the second row minus the first row, we get 0. -1 minus 3 is -4. and 1 minus -1 is 2, and 11 minus -9, careful with those double negatives, is positive 20. And then I'll do row 3 is row 3 minus row 1. And again, 1 minus 1 is 0. 2 minus 3 is -1. 4 minus -1 is 5. And 5 minus -9 is 14. So the next one, I actually really didn't want to divide out by -4 and get decimal there or fraction. So I actually swapped these two around. So I swapped to get that -1 up above. So I'm going to say row 2 equals row 3 times -1. So I'm basically taking that bottom row, putting it up in the middle and multiplying through a negative to get it to be a positive 1 there. Because I don't want to deal with fractions. And now I'm going to say that row 1 equals the old row 1 minus 3 row 2. And when I say row 2, I'm not talking about these ones. I'm talking about this new row 2. So I've got here 1 minus 3 times 0 is 1. And then, 3 minus 3 times 1, of course, is the 0 that I want in that spot. And then I've got -1 minus 3 times -5. So that's going to give me positive 14. And then I've got -9 minus 3 times 14. So that's plus, when you do the double negative, careful there, you get 33. And now I want to clear out the bottom. So row 3 equals the old row 2 plus, and I kind of in my solutions did this, plus 4 times row 2 new, just to kind of make sure it's super clear there. So here I'm taking 0 plus 4 times 0, of course, is 0. Then I've got -4 plus 4 times 1 is 0, which I wanted. And now I have 2 plus 4 times -5. So that's plus -20. I get -18. And then I have 20 plus 4 times -14, which is -36. And this worked out pretty well for me because now I can get a 1 in the row 3 column spot, and just by dividing out that -18 and not end up with fractions. So row 3 equals row 3 divided by -18. So I get 0, 0, 1, 2. And then row 1 is row 1 minus 14 row 3 to clear that one out. So I have 1 minus 14 times 0 is 1. 0 minus 14 times 0 is 0. 14 minus 14 times 1, so 14 there minus this guy, will get me that 0 in the top right that I want. Now I've got the only one kind of with actual numbers. I have 33 minus 14 times 2, which is 5. And then I'll do row 2. I had a -5 in that last column that I want to clear out by adding 5 of those guys. So I'll see that that's row 2 plus 5 row 3s. So this one will stay a 0. That one's going to stay a 1. That -5 plus the 5 ones zeros out. And then the one with actual numbers, I've got -14 plus 5 times 2, which is -4. So we've come out that we have a point of intersection of the planes, which is case 8. I'm just going to stop there and do the second half of the solutions in another video.